Greetings, everyone. Time to continue in the chapter about exponentials. The next development we need to talk about are logarithms. Now, before we actually get to the logarithm functions, what we need to talk about really is, what is a logarithm? Okay? And if you've seen one before, great. And if you haven't, this will be good for you. And if you have seen it before, again, this will be good for you too. Just to kind of hash out and flesh out all those wrinkles, right? Okay, so let's start with some of the basic operations here. If I give you 2 plus 3 is equal to 5, right? An addition fact. Don't forget that there are other ways of writing that same fact that all have the same meaning, but maybe just a different, question that may come with it, or a different way of phrasing is really all it is. Okay, so for example, 2 plus 3 equals 5 has the ability to commute, right? So 3 plus 2 is also equal to 5. And then the same information can be written with an opposite of subtraction. 5 minus 3 is 2, and 5 minus 2 is 3. Okay? I can do something similar with a multiplication fact. 4 times 6 is 24. Has the ability to commute. So 6 times 4 is 24. Okay, well, the same information can then be rewritten. 24 divided by 6 is 4, and 24 divided by 4 is 6. Since both of those operations, addition and multiplication, have the commutative ability, the ability to commute, I only need one opposite. For addition, it's just subtraction. For multiplication, it's just division. And it can be used in two different ways, depending on if I want to get the 2 as the answer or the 3 as the answer. I could use two different subtractions from the same fact. Same thing here. If I want to have the 4 solve for, or the 6 as the answer, I can do division two different ways with the same fact. Okay? Those have the ability to commute, so the division has an ability to be written two different ways from the fact. Okay, now we move on to exponents, the things we've really been talking about, right? Something like 9 squared is 81. Okay? Now, of course, the opposite of that would be the square root of 81 is 9. But notice the exponent and the base do not have the ability to commute, right? So 2 to the 9 is not going to be 81, right? It's just like 9 squared is 81. You can't just switch it and get the same answer. So by the same light, I can't take radicals and reverse it around, the 9th root of 81 to give me 2. That won't work. Since the original operation does not commute, then the opposite operation that you're doing won't have a second way to be written. It won't have a way of mirroring it around. So then that leaves a big hole here. Everywhere else, I was able to find some way or another to isolate the any given number in the fact, right? Here, there's a big gap. In this fact, 9 to the 2 power equals 81, I need a way that I can isolate the 2 to say, oh, I've solved for that quantity, right? Some sort of calculation is missing here. That means that your arithmetic facts are incomplete unless you include logarithms. And here's what we do. We rewrite exponential setups, right? Base, power, answer, okay, as a logarithm with a base that matches the base of the exponential, right? But it's equal to the power, and the logarithm is something that's acting on the original answer there. In the logarithm, it's called the argument, right? So right here, you're meant to think of this logarithm as acting on that 81. And then 2 is the result. Okay? So what really is a logarithm? By this determination, you should be seeing that what they do is they calculate exponents. Without logarithms, we don't have a way of isolating things that are considered to be exponents. Okay? So I need logarithms in my arithmetic fill, right? In my, please excuse my dear Aunt Sally, and then you fill in radicals and logarithms and all the ones that aren't in the limerick there. Okay? You've got to have them in your tool belt as one other operation that the arithmetic needs. They calculate exponents, okay? So then I've got this generic logarithm piece here, and this is what I want you to do when you approach one of these. You read it out loud. The log base c of x is p. That's how you read it, okay? Log base c of x. It's acting on x. But when you're approaching one of these problems, what you should be really thinking to yourself is, what power, what exponent turns c into x? The answer to that question is p, right? So what exponent transforms c into x? In this case, it would be p. So let's read this one over here. The log base 9 of 81 is 2. But then what does that mean? What power turns 9 into 81? The answer to the question? 2. 2 is the power, 2 is the exponent that transforms 9 into 81. So that's the answer to that particular logarithm. Let's work some more logarithms out by just using the multiplication facts we already know. Okay, so log base 10 of 100. Remember, we're asking ourselves, what exponent transforms 10 into 100, right? What exponent transforms 10 into 100? 10 squared equals 100, doesn't it? So the log base 10 of 100 would have to be 2, because 10 to the 2 power is 100. Don't forget, the answer to a logarithm is an exponent. Okay? Next, log base 3 of 9. Well, don't forget that 3 squared is 9. So log base 3 of 9 would need to be 2. Right? Okay. Next, log base 4 of 64 would be 3, because 4 to the 3 power is 64, right? 4 times 4 times 4 is 64. All right. Log base 2 of 32. What exponent turns 2 into 32? So 2 times 2 is 4, times 2 again is 8, times 2 again is 16, times 2 again is 32. Oh, it must be 5, right? 2 to the 5th power is 32. Okay? Log base 5 of 25. Okay? We're back to the easier ones like before, right? 5 squared is 25. So log base 5 of 25 would need to be 2. Okay? Now the reason why I bring that up is because of this next one. There's some little tricks to doing these things, other alternate methods, right? Not tricks, but so we know that the log base 5 of 25 is 2, right? So how could I transform a 5 into a 1 over 25, right? Don't forget, there's a type of exponents that we deal with that make things do reciprocals, right? Negatives. So look, 5 squared is 25, but it's in a division, it's in the denominator. So this would be negative 2, right? Because 5 to the negative 2 is 1 over 25. Okay, so look, anytime you do a reciprocal of either the base or the argument in a logarithm, it changes the sign of the result. Okay, here's another little side parlor trick right here. If you swap the base and the argument, see down here it was log base 5 of 25, here it's log base 25 of 5. Then it reverses the process. Instead of going up in an exponent, it's like going down like a radical would, okay? And what happens is you get the flip of the answer. Instead of 2, I get 1 over 2, okay? Let's dive into that another way. 25 raised to the 1/2 power. Don't forget the 1/2 power is like a square root, right? 1 power 2 root. So 25, the square root of 25 is 5. So that's definitely true. The log base 25. What power turns 25 into 5? That would be a half. Okay? So anytime you reverse the base and the argument, it's just going to flip the answer. Okay? If I flip one of the bases or arguments, it changes the sign of the answer. Okay, well let's slap out these last two here. Log base 3 of 81. 3 times 3 is 9. Times 3 is 27. Times 3 again is 81. Oh, there we go. So it must be 4. Because 3 to the 4th power is 81. Okay? Now in this next one, I'm going to use the little methods that I had up here. I've swapped the 81 into the base, which means it's going to flip the answer. Also, I changed the 3 into a 1/3, which means it's going to change the sign of the answer, right? It's like putting both of these two methods together. So look, swapping it makes it 1/4 instead of 4, and flipping one of these makes it negative instead of positive. So the log base 81 of 1/3 would be negative 1/4. Okay? All right, so some other basic ideas behind logarithms are going to be some of these special rules that come up. The log base anything of 0. Okay, well, you got to be careful here. Logarithms, a lot like division, can't handle 0. Okay, because you're asking this question. The anything, the a, raised to what power equals 0? Okay, think back to your exponential functions. Remember, they never actually hit the axis. They had an asymptote. They never intersected the axis. That means this is not possible, right? No possible answer. So right here, the log base anything of 0 is undefined. Okay? The log base anything of 0 is undefined. It's like dividing by 0. You do not take the logarithm of 0. Okay? We also don't do the base of 0, but just because it's trivial. Okay? Next, the log base anything of 1. Well, that's asking yourself anything to what power would give me an answer of 1. Well, we have something for that, right? There is an exponent that we put here that will turn anything into a 1, and that's 0. Anything to the 0 power is 1. So the log base anything of 1 would have to be equal to 0. Okay? And then last one here on this side, the log base anything of the same thing equals 1. Let's think about that for a second. I'm asking what exponent transforms a into a, right? Well, 1. Anything to the 1 power gives itself back. So what transforms a into a? That would be 1. Okay? Now let's talk about actually calculating some logarithm values that are not just the straightforward ones from your times tables, right? Being able to calculate any logarithm is going to be important eventually to solving all of the problems with any exponent that can be possible. So let's start with the default bases, okay? Log with a base of 10 is the default original logarithm base that was invented hundreds of years ago because of our base 10 counting system, right? We have 10 fingers, we count by tens. In our number system, there are 10 digits to any place value. So base 10 was our original default to logarithms, okay? So if you see a log with no base written on it, log, no base, it defaults to base 10, right? And you'll notice on the calculator, there is an actual log button. That's base 10 logarithm, okay? So the log of just 100, that's what power turns 10 into 100. We already did that one a little bit ago. It equals 2. Or if it's a not so easy logarithm, the log base 10 of 4, I can compute just by doing the log of 4. So in the calculator, I would hit log of 4, and I get 0.602. Like so. Okay. Next, a more recent default. In our more recent technology, the last couple of last 200 or so years, a lot more logarithms are used with exponents that deal with the natural number e that we discussed in the last lecture, right? So a log with e as the base has been abbreviated to ln, right? Natural logarithm is sort of the way they were going for it there, but they wanted to start with the L. Okay, it's sort of French. And the log base e of something like 7 would then be the ln of 7. Okay, it has no different properties. It's just an abbreviation so that I don't have to write log base e all the time. Okay, so that's what this means. What power turns e into 7? That's what ln 7 means. Okay, and in your calculator you'll notice there is an ln button. So I would hit ln 7, and that's 1.94 591. Da 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 da. Okay. Now, of course, most of these numbers that you're going to calculate with these logarithms in the calculator are going to be irrational numbers. Every once in a while, you'll run into a nice whole number or at least a rational, but for the most part, you're going to get a lot of these types of decimals that go on forever with no pattern. Okay, and that's why this is really essential. The calculator is not just a time saver anymore. It is going to be essential to all of the problems that we're going to solve. Okay, so here's how you use your calculator to do any logarithm. You should have noticed there is no generic logarithm button on your calculator, and that's because they didn't need to program one. On this calculator, you just need any logarithm button. It doesn't have to be generic. It could be any base. And that's because I can change the base of any logarithm to any other base. Okay? Here's the actual formula for it. Notice I can take log base a of x, and I can just turn it into a division where x and a are still in there, you know, with the arguments of two separate logarithms. And this p is there. That means I can choose some base on this side as long as it's two of the same base. Okay? Here's a much simpler way of looking at it. I prefer ln because it's just less writing. Log base a of x, you can take any logarithm, and then really you just do the ln of the x part divided by the ln of the a, the base part, right? And then you can do any logarithm you want. So let's get an example here. For example, let's say I wanted to answer the question, what power turns 3 into 7? Right? Well, remember, exponents are found with logarithms. So what am I asking here? I'm asking what power log base 3 of 7, right? What power turns 3 into 7? That's the question that I'm answering. But according to my base change formula over here, all I really need to do is ln of 3 divided by ln of 7. Side note, not the ln of 3/7. Oops, I made a boo-boo. ln of 7 over ln of 3. Okay, not 7/3. Those ln's do not wipe out. I cannot merge them in any kind of way. I simply do both of these calculations. In the calculator, if you do it all at once, it's going to put parentheses around each argument. Okay, so ln of 7, parentheses, divide by ln 3, parentheses, and I get 1.77124. That's good enough. Okay, so what does this really mean? Don't forget what it means. If I take this number here and I put it in this exponent, if I take 3 and raise it to this power, check it. 3 caret, like raised to this power, should give me back 7. And that's what we're finding with logarithm there. We're finding exponents. Now to get to what we were really trying to push forward for right here. Logarithmic functions are what we really were study here and use. So let's take all of those properties that we were just talking about and apply them into a function now, right? So logarithmic functions have the format f of x equals log base something of x, right? And a will be just some number, some positive, non-zero, usually not one number, right? Okay. The good news about these is that you already know plenty of information because you've studied exponential functions already, right? So all the stuff that you know about exponents carries over to logarithms directly because logarithms are directly related to exponents, to exponential functions, right? So what happens is the logarithmic functions are just the inverse of those exponential functions, right? Remember, inverse means that if you swap x and y and solve for things and then rename the function, that one function turns into the other, basically. Also, it takes any pairs and swaps them, right? So same thing. If you have some exponential function with some base a, its inverse will be the logarithmic function with base a. There'll be inverses. Well, okay, so let's take all that we know about the exponential graph right here, right? These were the exponential graphs. They go through that center 0, 1. They have a horizontal asymptote on one side. The domain was all real numbers, and the range was 0 to infinity. Okay? So if you do the inverse, remember the way we do that is we draw that line, y equals x, right? And we mirror image over that line. So I'll take this graph right here and I'll flip it across the line this way. And this is what we get. Instead of 0, 1 as my center, the center for a logarithmic function is 1, 0. Instead of a horizontal asymptote, flips over from here to here. And I now have a vertical asymptote. Important. Logarithm functions have a vertical asymptote at 0. Okay? Remember from last chapter, vertical asymptotes occur because of some sort of undefined. And we've already hit that. The logarithm of 0, no matter what the base is going to be undefined. And that's what's happening. I'm getting a vertical asymptote here. Okay? So the center is now 1, 0. I have a vertical asymptote on this side. And the domain and range have swapped. The range is now all real numbers, and the domain is only from 0 to infinity. Okay? We don't do logarithms of 0, and for this that we're studying, we stay away from logarithms of negatives. Those tend to be imaginary and complex. Okay? Now let's graph some of these functions using the information that was just discussed, right? So I have all of this information on any basic logarithm graph. So now we're going to graph a few using the transformations. So let's start with just a basic logarithmic function, right? I don't care that the base is 3 unless I'm comparing it to other logarithmic graphs and other things like that. You're not going to be able to tell the really fine curvature on this thing. So when I put my grid up, I remember that I've got a center of 1, 0, and it's not changed, so it's still there, 1, 0 center. And I remember also that I have a vertical asymptote at x equals 0, which is still there, it's still here. Okay? So then now I just draw my shape. It's traditionally, like the original, hugs from the bottom, hits that point, and then takes off to the right. Okay? Now side question. Does this flatten out like a square root seems to do? Now technically square roots don't flatten out either, but neither one of them flatten out. This actually does go all the way up to infinity, right? The range does go up forever. It's extremely slow. Okay? So just hook it out to the direction like that, but it does slightly go up. Okay? All right, next. Again, log base 7. Unless I'm comparing it to other pieces or if I'm doing any calculations, I don't actually care too much about the actual 7 itself at this moment. Instead, I'm going to focus on the other things, like the plus 2 and the plus 4, right? The plus 2 here, this is going to be a shift left. The plus 4 is going to be a shift up. Okay? So let's put my grid up. My center originally started out at 1, 0, and I'm shifting left, which is going to subtract 2 from the x, and shifting up 4, so plus 4 to the y. My new center is negative 1, 4. Okay, so negative 1, 4. There's my new center right there. Okay, now my asymptote, my vertical asymptote was x equals 0. If I shift that up or down, that doesn't affect a vertical asymptote. But if I shift it left or right, that does. I shifted it left. So my new vertical asymptote is x equals negative 2. Okay, and there's another check for that, by the way. Remember what we said about vertical asymptotes. They cause some sort of unknown or undefined. Okay? Remember, logarithms can't handle 0, so you ask yourself, what number would make this inside 0? In this case, it would be negative 2, right? So negative 2 is the unknown value. It's the bad number here. Hence, negative 2 is my vertical asymptote. Okay? So now let's draw the graph. I'm going to hug the asymptote at the bottom, and I'm going to keep hugging it pretty close until I get to that center, and I'm going to sort of just hook out to it, and then I'll just keep hooking out to the right there. Okay? Next, let's take a look at all the pieces here now. I've got the 5, the minus, and the minus 1 here. What base is that? Base 10, right? Remember, there's not a base written on the LOG, it's base 10. All right, so now let's do my pieces here. X minus 1, that means this was shifted to the right. Plus 5 here, right? That means this was shifted up. And then look, there's a negative on top of my function on the outside. This is a vertical reflection. Okay, a vertical reflection there. So let's see. Let's go through all of this. My center point, right? My center started out at 1, 0. It got vertically reflected, right? Up and down. So the vertical reflection would change the sign on your y value. It just so happens that my y value was 0, so it didn't affect it. But then I shifted it right 1, so plus 1 to the x, and up 5, so plus 5 to the y. My new center for this graph is now 2, 5. Okay? Where's my vertical asymptote, right? What causes 0 in here? My vertical asymptote is going to be x equals 1. So let's draw this in. Let's see, 1, 2, like this. Vertical asymptote here at 1. And my new center is up 5. Ooh. That's like way up here. All right, let's draw it in. This time, let me get this out of the way for a second. Let me draw a little more here. It's important this time to notice that since it was vertically reflected, right, that negative, instead of hugging at the bottom, it's going to flip vertically. It's going to hug from the top. So instead of doing this, right, it's going to do this. It's going to hug from the top. It's going to do like this. And still hook out to the right there. Okay? Because of the vertical reflection. All right. One more. I don't see too many things changed, right? However, you do need to notice there is a shift right here. The 4, that's a shift. But which way is it? Also, the negative here is a reflection. But it's on the inside with the X. So that's a horizontal reflection, a left and right reflection. Also, what number causes this to be? 0, right? Since 4 causes this to be 0, this is actually a shift to the right. And it also tells me that my vertical asymptote is x equals 4. Okay? It's a shift to the right 4 because of the reflection. Normally, a plus 4 would be a shift left, but this time, because of the reflection, it gets turned around. Okay? And those are the only two things that changed here. So let's see. Let's calculate my new center. Center starts out at 1, 0. A horizontal reflection would take the x value and flip its sign. That's what horizontal does. It changes the x signs. Next, it got shifted to the right 4. So plus 4 to the x would give me 3, 0. Okay, so let's graph it. One, 2, 3, 4. We'll put a couple of here and here for good measure. X equals 4 is my vertical asymptote. Like so. 3, 0 is my new center. So that's here. Notice it's on the left-hand side of the asymptote this time, whereas all the other ones are on the right. That's a dead indicator, right? However, it was not vertically reflected, it was horizontally reflected, which means it's still going to hug at the bottom. And then when it hits that center point, it's going to hook outwards. Right, that way. I could be a little off with that one right here, so I probably don't want to mark those. I don't know exactly. We didn't calculate it, right? Okay. Okay, so I hope this helps you in understanding logarithmic functions better.